This is Thermodynamics video 8 with Lars-Erik, and it is an overview over UP, BubbleT, and UT calculations. We have an overview of VLA, vapor, liquid, equilibrium, calculations, the ideal. So far we only worked with ideal conditions. We have BubbleT, BubbleT calculation is easy and explicit. We have view P, which is medium difficult, but still explicit. We have BubbleT, which is medium difficult and it needs iteration. And we have a UT, which is medium difficult, and then we also have the flash calculation, which is more difficult and also needs iteration. So these 5 types of calculation, they have increasing difficulty from a BubbleT calculation to a flash calculation. Then I start with UT because we had that in the last video. This is the UP calculation. P equal 1 over the sum of yi over pi sets. That is an explicit formula. That was the one that we produced last hour. Then we go to the BubbleT calculation. And that is quite simply that the pressure is the sum of the partial pressure, which is the sum of x, y times EI set. And I claim that this is the easiest calculation. That is because I remember this equation. I remember that the pressure is the sum of partial pressure, which are defined by Raoult's law to be the mole fraction times the saturation pressure. This one is a little more difficult to me because I do not remember this equation. So if I should do this without a textbook, then I have to deduce that equation to make the explicit calculation. Then we go on to BubbleT calculation. With a BubbleT calculation, we talk about a specified pressure and mole fractions in the liquid. The problem when we do not know the temperature is that we do not know what the saturation pressure is, because then we have to know the temperature. So to achieve this, we guess a temperature, then we calculate the saturation pressure for all components. Then we calculate the mole fractions in the vapor as Pi sat times xi divided by P. Then we calculate the sum of the mole fractions in the vapor. And if the sum of mole fractions is equal to 1, then the guessed T is okay. Else, try a new temperature. And if I ask you on an exam to do this, this is how I prefer to define an iterative calculation in this way. Then we have one more calculation left, and that is the BubbleT calculation. That is based on specified pressure and mole fractions in the vapor. Again, we have the problem that we do not know the saturation pressure because we do not know the temperature. So an easy way to start is to guess the temperature, then calculate the saturation pressure as a function of the temperature, then calculate xi as P times yi divided by Ti set. Then calculate the sum of all the mole fractions in the liquid. If the sum of x's equals to 1, then the guessed T is okay. Else, try a new temperature. So, what I have tried to do is to give an overview over all these calculation principles to calculate QP, BubbleT, and UT. Some of these are explicit and easy, some of them are more difficult. We have explicit formulas for UT calculations and BubbleT calculation because we know the temperature. And in the BubbleT and UT calculations, we do not know the temperature. And then an easy procedure is to guess it and then calculate it and check that the sum of fractions equals to 1. So that is the end of video 8. This is video 7 in the thermodynamics with Lars-Erik, and this is about derivation of UP calculation. That is how to calculate pressure when T and all y's are known. That is, we know the temperature and we know the composition in the vapor phase, and then we should calculate the pressure. And all the saturation pressures as a function of T are easily calculated. We assume that we have an Antoine equation or shortcut equation or something like that, and we assume two phases. That is liquid and vapor. And the equations we base this on it's y times p equal xi times pi set. That is law, or actually it is Raoult's law combined with the definition of partial pressure. And we assume that the sum of mole fractions in the liquid is 1. We also assume that the sum of mole fractions in the vapor are constant. However, that is defined in the task. From that, xi is yi times p divided by p I saturation. The sum of x's is then the sum of yi times p divided by pi set, and then the total pressure can be put outside. P times the sum of yi divided by set. And one of the equations was that the sum of mole fractions should be 1. And then we end up with the equation of the total pressure is 1 over the sum of yi over pi set. So we can calculate P explicitly when T and all y's are known. So this was the derivation of UP calculations for ideal conditions, and that ends video 7. We can start. This is the video 6 in thermodynamics with Lars Erik, and this is a short summary of two-component equilibrium. We start with the saturation pressure for a pure component. And that can be estimated as the P sat as a function of temperature. Then we have something called ideal liquid, which is the same as Raoult's law. And for a two-component equilibrium, it says that the total pressure is the mole fraction of the first component times the saturation pressure of the first component plus the mole fraction of the second component times the saturation pressure of the second component. And that is ideal liquid. And then we have the gas partial pressure. That is a definition of what is meant by a partial pressure. That is that the total pressure is the partial pressure of component 1 plus the partial pressure of component 2, which is the vapor mole fraction of component 1 times the total pressure plus the mole fraction of the second component times the total pressure. And then Raoult's law can also be expressed by P I equals y I times the total equal to x I times p sat I. It is just a combination of the definition equations. Then we have, this is just the definitions of Raoult's law and gas partial pressure. And then we have binary phase diagrams to give an illustration of what we are talking about. We have a temperature as a function of mole fraction, and it can be both the liquid and the vapor fraction. The pressure is constant, and if this is 0 and this is 1, we have, it looks about like this, where this is the bubble line, this is the dew line, and these 2 points are in equilibrium. And we have another type of diagram, which is a pressure as a function of mole fraction. And in this case, the temperature is constant. And in that case, we have the bubble line and the dew line. Dew line and the bubble line. and here we have two points in equilibrium. So this is just a short summary of the introduction to two-component equilibrium. So that is the end of video 6.